You need to know that things can turn directly from a solid to a gas. That's called sublimation. For instance, dry ice does that. You also need to know that things can turn directly from a gas to a solid. That's deposition. For instance, your car in the winter, if you leave it outside, you'll usually come out in the morning and there will be frost on the windshield, even though it didn't snow, even though your car never got liquid water on it. It's just that gaseous water in the air, water vapor, when it hits the really cold car, it can latch onto some other water molecules and turn directly to a solid. All right, know that state and phase are the same thing, by the way. Okay, I pointed out on the last slide that evaporation and boiling are not the same term. That's because boiling refers to essentially the situation where you have really quick evaporation and you have bubbles like forming at the bottom and rising to the top. Only use the term boiling when you really mean boiling. If you leave a glass of water out on the counter for a week, it'll eventually all go into gas form. That's called evaporation because it never actually got hot enough to boil during that time. The most important part of this curve, I think, is the flat sections. It's where the phase transitions happen. But you do need to know that the solid is at the low temperature and low energy, liquids at medium temperature, medium energy, gases at high temperature, high energy. All right. It ends up those flat sections tell us a lot about the intermolecular forces going on behind the scenes. Because the flat section means that the energy is changing, so you're putting energy into the substance or you're taking energy out, but the temperature is not. So energy is changing, but temperature is not. That's weird. So where's that energy going or coming from? Well, it's actually the intermolecular forces. So let's look at the solid. When an ice cube melts and turns into a liquid, the temperature can't go up until all the ice has melted. That's what I call at least the iced coffee effect. Same thing when a liquid turns into a gas. You can't get the temperature go up till all the liquid's gone. There's actually a cool thing you can do at a campfire. If you put water inside a leaf and then put it over the fire, the leaf won't burn because the water will prevent the temperature from getting higher than the boiling point of water, and that's not high enough for the leaf to burn. Now, the parts of the leaf that aren't touching the water will burn, but the part of the leaf touching the water won't. Kind of cool. By the way, don't do that unless you know what you're doing and you're safe and you have help and you have fire extinguisher nearby, and yeah, just don't do it. All right, so the length of those lines has to do with the intermolecular forces, because during that time, the energy is doing something. It's breaking the intermolecular forces. It's not increasing the temperature. It's not making the particles go faster. So breaking those intermolecular forces requires energy. The temperature can't increase until all the particles have undergone the transition, and it's pretty much when you're increasing the energy, you're breaking the attractions, and when you're decreasing the energy, you're letting them attract back together. All right. You also need to know something about melting and boiling points. This is the place where those transitions happen. It's the temperature transitions. You need to know that water melts at 0 degrees C. You need to know that water boils at 100 degrees C. That's also the temperature at which water freezes and water condenses. But remember, this is just for water, not for anything else. But you can use those two pieces of data to make a number line and to figure out what state of matter something's in at any particular time. So this is a number line, goes from low numbers to high numbers. Let's look at the example of mercury. Mercury's melting point is negative 39. So I'm going to put negative 39 degrees C here. That means at a lower temperature than that, mercury is a solid. And at a higher temperature than that, mercury is a liquid. Mercury's boiling point is 357 degrees C. So I'll put 357 here. That means below 357, mercury is a liquid, and higher than 357, mercury is a gas. All right, so the question here asks, what state is mercury at negative 50 degrees C? Well, the only question is, where is negative 50 degrees C on the number line? And I say it's here. That means at negative 50, mercury is a solid. What about at 101 degrees C? Well, I'd say that's about, what, here, 101? that's very firmly in the liquid range. Right? For water, the answers would be different because water's melting and boiling points are different than mercury. All right, I want you guys on your own right now, think of ethanol. Try the ethanol problem. Pause this video if you need to come up with the answers. All right, here we go with the answers. At negative 50 degrees C, ethanol, that's between ethanol's melting and boiling point, which means that at that temperature, ethanol is a liquid. So negative 50 degrees C, ethanol is a liquid. At 80 degrees C, that's above the boiling point. So ethanol is, in fact, a gas at 80 degrees C. That's it for the video for today. Remember that you do need to know a lot about the states of matter that I haven't necessarily gone over. You need to know the basics on your own. So go look that up somewhere online or in a textbook if you don't know